Okay, so we are going to pick up where we left off on 2D kinematics. So last time where we left off, we were looking at descriptions of motions and determining if acceleration is constant. So in order to do that, we have to take our position function and we need to look at the second derivative because our second derivative of position is acceleration. So here I have that x is equal to negative 3t cubed minus 4t. So my velocity, which is going to be the derivative of position, is going to be negative 3. Then I'm going to kick this third power out. We're going to have t squared minus 4. So my acceleration here is going to be, that's going to be negative 9. And I'm going to kick the power out, so times 2t. The derivative of negative 4 is 0, so I'm going to have negative 18t. Okay, that's not constant. That's still a function of time. So if I look here at the y, I get that my velocity, which is going to be my derivative, in the y direction is going to be negative 10, because I kicked that 2 out, so 5 times 2 is 10, t. My derivative of 6 is 0. So my acceleration is going to be negative 10. Now, these look a little bit different. These have those I hats and j hats. So I'm going to look at each one specifically. So my velocity, now here we're going to have velocity as a vector. So I'm just going to look at this piece, 2t squared. So I'm going to kick the power out. That's going to be 4t when I take the derivative, and that's going to be in the I hat or the x direction. My y direction I'm going to get by looking at the derivative of this piece right here. So I'm going to have negative. The derivative of 4t is 4. The derivative of 3 is 0, so I've got negative 4j hat. So my acceleration is going to be a vector. Again, it's going to be the derivative of this with respect to time. So I'm going to have derivative of 4t is just going to be 4. And that's again going to be in the I hat direction. Derivative of 4 is 0, so my acceleration is just 4. This would be in meters per second squared in the I hat direction. Similarly, this bottom one here, to get my velocity, I'm going to take the first derivative. So I'm going to take the derivative with respect to time of this piece right here for my x. So I'm going to have 4. Kick the power out, that's going to give me 3t. I subtract 1, giving me a square, minus 2. That's going to be in the I hat direction. And my derivative of 3 is just going to be 0, so that means my velocity is only in the x direction. My acceleration, I'm going to have the derivative of this again. I'm sure by now you've noticed a pattern, so I'm going to have 4 times 3 is 12. I'm going to kick that 2 out. When I subtract 1, I still have a t. My derivative of 2 is 0. So this acceleration is a function of time. So in order for the acceleration to be constant, my position function has to be no higher than a t squared term. So it has to be t squared or less. Because that's the only way we're not going to have a t in the acceleration when we do two derivatives. All right, so let's scroll down here. Let's look here at another example. We have a rabbit running across a parking lot. And strangely enough, some weird, evil physics person has maybe coordinated to have some grids drawn. Who thought? So we have the rabbit's position. Here's his x coordinate right here. And his y coordinate is right here. That's the functions. So we want to know at t equals 15 seconds, what is his position vector? in terms of both unit vector notation, now that's going to make this pretty easy, or in terms of magnitude and angle notation. That's not quite so easy. So let's look at just really what the position vector r really is. That's going to be his x coordinate in the I hat direction plus his y coordinate in the j hat direction. So for this unit vector notation at 15 seconds, literally all I'm going to do is I'm going to dump this negative 0.31 t squared plus 7.2 t plus 28. That is his position in the x direction. His position in the y direction is 0.22 t squared minus 9.1 t plus 30. That's going to be in the j hat direction. So this is his position vector at any time t. Now to make it extra special, we go, okay, 15 seconds. So what am I going to do? Boom. I'm going to say, okay, t is 15. So I'm going to go through here and I'm going to plug 15 in every single place I see a t. So if I come in here and I've got, okay, negative 0.31 times 15 squared plus 7.2 times 15 plus 28. That's in the I hat direction. I'm going to have 0.22 times 15 squared minus 9.1, that should be a minus, times 15 plus 30, and that's in my j hat direction. So I go to my random number generator and I start throwing information in. So I'm going to get the x is going to be about 66, and my y is going to be about negative 57. So my unit again is going to be meters. That is going to be my position vector. That's in unit vector notation. So it sounds really scary, super easy here. So for my magnitude, so my magnitude of r, I'm going to use my good friend Pythagoras. There's a reason we liked him so much in geometry class. So we're going to have 66 squared plus the quantity negative 57 squared, and then we're going to square root the whole thing. So that's going to be about 87 meters. I'm just going to ballpark to the nearest whole number here. Now, how am I going to get the angle? Well, remember, the angle is opposite over adjacent. So that means tangent of my angle theta is going to be the y over the x. If this is my theta, it's going to be my y over my x. So that means to find my angle theta, I'm going to need to use tangent inverse. That is second button on your calculator. My y is negative 57. My x is 66. So that's going to give me, again, rounded to the nearest whole number, about negative 41 degrees. Now that means that it is below the x-axis. It is this angle right here. That's what we're looking at. We're in quadrant 4. So what else could we do with this? Well, let's take a look. So if we wanted to find the velocity of this rabbit, so remember I said last on my position function was that negative 0.31 t squared plus 7.2 t plus 28. That's in the x direction, so that's an I hat. My y coordinate was 0.22 t squared minus 9.1t plus 30. And again, that's in the j hat direction, my y direction. So to find the velocity, my velocity is a vector. It's the derivative of that position function with respect to time. So what does that mean? Well, that means I'm going to start kicking powers out. So here, I'm going to kick that 2 out. So I'm going to have negative 0.62t plus 7.2. Derivative of 28 is 0. It's a constant. So that's my I hat term, my x term. My y term, I'm going to again kick that 2 out. So I'm going to have 0.44t minus 9.1. Derivative of 30 is 0. That's a constant. So that's my j hat term. So now to get the velocity at time equals 15, I just need to go in here, and everywhere I see a t, I need to substitute 15. So that means my velocity evaluated at 15 seconds is going to be negative 0.62 times 15 plus 7.2 in the x direction, and 0.44 times 15 minus 9.1 in the j direction, or the y direction. So we throw this into our random number generator because math. If we do that, what we are going to get is for our x component, this is going to give me about negative 2.1 meters per second. So it's in the I hat direction. In the y direction, I'm going to have about negative 2.5 meters per second. So that's going to give me my velocity at 15 seconds. So that tells me something about how the rabbit is running. Now, how am I going to get the acceleration? Well, you remember that acceleration is the time rate of change of velocity. So we're going to take the derivative of that velocity function with respect to time. So I'm going to go back up here to this function right here. There's a reason I wrote it down first. So I'm going to take that derivative. I'm going to have negative 0.62, that's in the I hat direction, the x direction, plus 0.44, and that's going to be in the j hat direction. That's going to be, of course, in meters per second squared. So we could find the magnitude, we could find the acceleration. At 15 seconds it is not changing, so that acceleration is going to be uniform. As weird as it sounds, that is uniform acceleration. And I could even find the angle at which that acceleration happens. So the angle at which that acceleration happens, I could find by using tangent inverse of the y component, which is the opposite, over the adjacent piece, 0.62. So I could find that that angle the acceleration is applied at is about negative 35 degrees. Now, because my x is negative and my y is positive, I'm in quadrant 2. So what you see is that my acceleration is pulling up. So quadrant 2, this is actually my angle. So right here, that's the reference angle. That's the negative 35 degrees. So this is the constant uniform acceleration that this rabbit is feeling as it's running through the parking lot, which is kind of strange, but it is a rabbit running through a gridded parking lot. So we're going to cut this video and we'll come back with some more examples in just a few minutes.